Mm. Hi everyone, good evening. So today we are going to start Turing machines. Okay, today we are going to start Turing machines. Good evening everyone. Good evening everyone. So this is the QR code of my compiler design textbook. This is the QR code of my compiler design textbook. This is the QR code of my compiler design textbook. You can buy it from PW store. This is the QR code compiler design textbook. You can buy it from PW store. And this will be helpful for GATE, BTech and MTech. Hi Shantanu. This will be helpful for GATE, BTech and MTech. Please scan the QR code and buy the book from PW store. And this is the QR code of my Telegram channel. Please join the Telegram channel. We do a lot of discussions there, right? So we have done almost 90% of TOC. I hope you liked it. And if you have any doubt in any topic, please rewatch the video again. I have made it so simple that you can understand it in one go. If you are not able to understand it, please watch it again. And whatever I taught in YouTube channel is going to be sufficient for GATE. This is not a crash course, this is a complete course. So I have completed everything, each and every topic. Only Turing machines is remaining. And Turing machines, generally we don't get questions. Very rarely we get questions, but still we'll complete it in a very detailed way. Okay. Okay. So yesterday we have completed context-free languages, and today we are starting with Turing machines. Today we are starting with Turing machines. Right? Right? Hi Prashant, good evening. It is almost good night. Okay. So 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 we are going to discuss recursive recursively enumerable recursive recursively enumerable languages and Turing machines. Recursively enumerable languages and Turing machines. Okay. So in Turing machine, what are we going to study? In Turing machine, what are we going to study? Right? What are the various things that we are going to study? So one is Turing machine theory, where we study about the theory of Turing machines. And the second one is machine to language of the machine conversion. Machine to language of the machine conversion. And the third one is language of machine to machine conversion. And fourth one is Turing machine as a transducer. Turing machine as a transducer. Turing machine as a transducer. Transducer means what? Converting input to output. Converting input to output. For example, you can give a number, two numbers, and you can ask the Turing machine to add both of them and give the result. So the input two numbers is converted to be the addition of two numbers. Okay. And then we are going to see countability. And then we are going to see Cantor's theorem. And then we are going to see Church thesis. Turing thesis. And then we will see variations of Turing machines. And then we will see variations of Turing machines. And then we will see variations of Turing machines. And then we are going to see reduction theorem. So if you see all this, then the Turing machines will be over. Okay. If you see all this, then the Turing machine is over. If you see all this, then the Turing machine is over. Right? Now, let us see recursive and recursively enumerable languages. Recursive and recursively enumerable languages. Recursive and recursively enumerable languages. One is definition. One is definition. Right. One is definition. So you are going to have recursive languages 1, recursively enumerable languages 2, and set of all languages 2 power sigma star. Set of all languages 2 power sigma star. Right? Let us say this is 3. Okay. Now what is 1? 1 is recursive languages. 1 is recursive languages. Hello Prince, good evening. Hello Prince, good evening. Hi Aman. Okay. So one is recursive language, and two is recursively enumerable but not recursive. 2 is recursively enumerable but not recursive, and 3 is not recursively enumerable. And 1 plus 2 is recursively enumerable. 1 plus 2 is recursively enumerable. Right? Now the question is, are there languages here? At these 2 points, are there languages? Right? So if you are going to say that there are some languages which are recursively enumerable but not recursive, then you should show some language here. If you are going to say that there are languages which are not recursively enumerable, there are languages which are not recursively enumerable, there are languages which are not recursively enumerable, you should show that. You should show a language which is not recursively enumerable, right? And these languages are not so simple. You cannot say a power n, b power n, c power n, something like that. So in regular and CSL, CFL, CSL, we have seen some languages, but these languages are, this is not very easy to prove give languages here and here, right? So there are only two languages given in any textbook, okay? So one language here and one language here, one language here and one language here, right? So the language given here, which is recursively enumerable but not recursive, recursively enumerable but not recursive. The language that is given here, which is recursively enumerable but not recursive, is the example is LU. The example is LU. LU means Universal Language of Turing Machines. LU means Universal Language of Universal Language of Turing Machines. Turing Machines, right? And then one language that is not recursive is also given, and one language that is not recursive is also given, right? One language that is not recursive is also given, not recursively enumerable, which means in 3, one language in 3 is also given. This is called LD. This is called LD. LD means diagonalization language of Turing machines. Diagonalization language of Turing machines. Diagonalization language of Turing machines, right? So LU means Universal Language of Turing Machines. LD means Diagonalization Language of Turing Machines. LD means Diagonalization Language of Turing Machines. Okay. So we have only these two examples, LU and LD. We have only these two examples, LU and LD. LU and LD. Right. We have only these two languages, LU and LD. That is sufficient. We are able to show a language which is recursively enumerable but not recursive, and which is not recursively enumerable. That is sufficient. That is sufficient, right? That is sufficient. And second thing is, we are going to see properties. 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 Now, what are the properties we are going to see is enumeration procedure. Enumeration procedure. Enumeration procedure, right? Enumeration means listing. Enumeration means listing. Enumeration means listing, right? And then membership procedure. Membership procedure. Membership procedure. Now membership means, given a string, does it belong to the language or not, right? And this procedure should work for both for members of the language as well as non-members of the language, as well as non-members of the language, as well as non-members of the language, non-members of the language. right? And then we are going to see lexicographic ordering. And then we are going to see lexicographic ordering. Lexicographic ordering. We are going to see lexicographic ordering. I'll tell you what lexicographic ordering is later. And then we are going to see closure properties. And then we are going to see closure properties. And then we are going to see L and L complement theorem. L and L complement theorem. Right? And the third one is undecidability problems in Turing machine. Undecidable properties. Undecidable properties in Turing machines. Undecidable properties in Turing machines, right? So I have already given you a table about decidability and undecidability. If you open the table and see, out of 40 problems, 27 out of 40 problems are undecidable. If you see the table, 27 out of 40 problems are undecidable, right? Now we are going to see 6 more. Now we are going to see 6 more. Now we are going to see 6 more, right? Now we are going to see 6 more properties. Right? Undecidability problems in Turing machine, 27 out of 40 problems are undecidable. 27 out of 40 problems are undecidable. 27 out of 40 problems are undecidable. Right? And we will see 6 more problems. We will see 6 more problems here. So undecidability problems are very, I will tell you one thing. In GATE exam, if you get a question about Turing machine, and if the question is about undecidability or decidability, if you blindly tick undecidability, 90% of the chances that it is right answer. Most of the problems related to Turing machine are undecidable. Okay, so blindly if you mark the question as undecidable, you will get a mark. Okay, so don't follow that blind method. I'm just saying, anyway we are going to see what are all the undecidable property, these problems related to Turing machine. Okay, 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 fine, fine. Yeah, Prashant, your question we will discuss. Okay, under the heading L and L complement problems, we will discuss your question. Prashant, please give me some time. I will discuss your question. We are going in a flow. So you have asked something which will come in the middle. Let me just continue this. When we reach that phase where you understand that question, I will definitely clear all your doubts. Till now in TOC course, I have cleared all the doubts. I have given examples for each and everything, right? Here also in Turing machine, I am going to give you everything. Okay? I am going to give you everything. Okay? Okay? We'll see 6 more problems. We will see 6 more problems, right? And then we will see Rice's theorem. 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 So this applies to all. This applies to only recursively enumerable languages. This applies to only recursively enumerable languages. This applies to only recursively enumerable languages. Recursively enumerable languages. Okay. Okay. So now, what is a Turing machine? Just like DFA, we have to define what is a Turing machine. What is a Turing machine? What is a Turing machine? Right? What is a Turing machine? So a Turing machine M is Q sigma tau. Some people call it as gamma also. Some people call it as gamma also. Some people call it as gamma also. Delta Q naught blank F. Delta Q naught blank F. Delta Q naught blank F. Delta Q naught blank and F. Yes, Yogesh. Alan Turing invented Turing machine. Alright. So Q sigma delta Q naught BF. Now I'll give you 3 minutes of time. I will give you 3 minutes of time. Yeah, Mohit, my health is fine. Thank you for asking. I'll give you 3 minutes of time. Write down what are all this and post it in the Telegram channel. If you can guess all this, it means that you are done with of 50% of the Turing machines, right? Write down what are all these in a paper. I'll give you 3 minutes of time. Okay. I'll give you 3 minutes of time. So what are the important topics for GATE 2026? You are from a Shrestha batch, is it? So first thing is be very comfortable with regular languages and context-free languages. 90% of the questions come from regular and context-free. But Turing machines is very easy. You will get 10% of the questions. Turing machines is don't leave it. Okay. Okay. So be very comfortable with regular languages and context-free languages. That is sufficient for GATE. But anyway, we are doing Turing machines also, which is very easy. So don't leave Turing machines as well. It is very simple concept. Okay, fine. So now tell me what are each one of this. Now tell me what are each one of this. Q, sigma, some people call it tau, some people call it gamma, delta, Q naught, B and F, right? So what is Q? What is Q? You know other machines, right? We have seen other machines, so you know what is Q. Yogeshwar, what is Q? Mohit, Prince. Sir, I am studying for the first time. No problem. One time is sufficient because I go from basics. Even if you are studying for the first time also, that is sufficient. Even if you are studying it for the first time also, that is sufficient. Okay. 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 So Q. What is Q? Mohit, Yogesh, Prashant, Prince. What is Q? You have seen all the machines so far. You have seen Q many times, right? You should be able to say what is Q. You know everything. I'm just trying to show you why it is not different from what we have learned earlier, right? This machine is similar to finite automata and push-down automata. You will understand how, right? What are the similarities? Let's see the similarities. Then we will see the differences. Okay. So what is Q? Forgot it. Forgot it. Very good, Prince. States. Very good. So Q is finite set of states. So Q is finite set of states. Finite set of states. Now what is sigma? Now what is sigma? Now what is sigma? We also have seen sigma. Very good. Sigma is alphabet. But here we have to say input alphabet. Sigma is input alphabet, which means what are the symbols that are allowed in the input? Sigma is input alphabet. Sigma is input alphabet, right? So like that, please write all of them. Like that, please write all of them. Okay. Okay. Like that, please write all of them. Q, sigma, delta. Like that, you think about each one of them, right? This tau or gamma, you don't know about it. This tau or gamma, you don't know about it. Let's leave it. What is delta? What is delta? Delta you have seen many places. Delta you have seen in many places, right? What could be delta? Now you are seeing all the common things first. Later we will see the things that are different. Very good. Delta is transition function. From one state, how we are transitioning to the other state. From one state, how we are transitioning to the other state. Transition function. Delta is transition function. Delta is transition function, right? And then Q0. What is Q0? This also we have seen in all the machines so far. So you know almost everything, right? I don't have to teach. What is Q0? What is Q0? Very good. Q0 is initial state. 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 Right? What is B? So this you might not know, but F you may know. But F you know this. But F you know this. What is F? We have seen it in all the machines. So you see that except two things, all the remaining things you already know, right? I don't have to teach. Except these two things, tau and blank, you know all the remaining things, which means you know what is a Turing machine. Very good. It is set of final states. There can be more than one final states. That is why I am saying set of final states. And what is the relationship between Q and F? What is the relationship between Q and F? Between Q and F, what is the relationship? 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 Very good, Yogesh. There can be many final states possible, but there will be only one initial state. There can be many final states possible. There can be many final states possible. There can be many final states possible. Right? So what is F? F is set of final states. What is the relationship between Q and F? So these final states are nothing but subset of the set of states. Total, out of total states, some of them are going to be the final states, right? And in a transducer, you know, you don't need any final states. You might have seen this Mealy and Murray machine, right? Long back, maybe 3-4 months back, I taught you Mealy and Murray machines. In Mealy and Murray machines, they are transducers. There is no need of final state. Similarly, when you are using a Turing machine as a transducer, final state can be empty, which means there is no need of final states. We are just converting the input to output. We are just converting the input to output, right? Fine. Now there are only two things that are remaining. One is tau or gamma and the other one is B, right? So what is tau is set of tape symbols, set of tape alphabet, or I can say set of tape alphabet. So what is sigma input alphabet and tape alphabet is input alphabet can be A comma B, input alphabet can be A comma B, right? Which means when you start the Turing machine, you are going to have only on the tape, you are going to have only A's and B's, right? And to the left of input and to the right of input, there will be infinite number of blanks. To the left of input and to the right of input, there will be infinite number of blanks, right? So what is B? B means blank. Blank symbol. B means 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 blank symbol. Right? So now tau can be on the tape. There can be AB, because AB are in the input, therefore definitely AB will be there. There will be blank because it is a blank state. Along with that, you can add any other symbols. For example, I will make this A as X, make this B as Y when I am doing some transactions. Right? Right? So what is the relationship between sigma and tau? Sigma is a subset of tau. Right? Sigma is a subset of tau. Sigma is a subset of tau, which means input alphabet is a subset of tape alphabet. Input alphabet is a subset of tape alphabet. Input alphabet is a subset of tape alphabet. So this is a Turing machine. Now depending on transition function, we can define deterministic Turing machine and non-deterministic Turing machine, just like how we did in finite automata. In finite automata, if you remember, we have deterministic finite automata and non-deterministic finite automata, right? In finite automata, we had deterministic finite automata and non-deterministic finite automata, right? Right? Deterministic finite automata and non-deterministic finite automata we had. We had deterministic finite automata and non-deterministic finite automata, right? Similarly, here also we have deterministic Turing machine and non-deterministic Turing machine, right? If sigma is, if delta is q cross, which means I will be in a state and I will see a tape symbol q cross tau to q cross tau, which means I will go to some state and I will write something in the tape, and then I can move either left or right, and then I can move either left or right. So on seeing a tape symbol, I will go to some state, I will change the tape symbol and I will move either left or right, and I will move either left or right. I will move either left or right. I will move either left or right. Right? Now this is called as deterministic Turing machine. Why is this called deterministic Turing machine? Because we are exactly saying that on seeing in a some state, on seeing some symbol, we are going to some state, exactly one state. We are not saying that make a copy of yourself and go in two ways like NFA or non-deterministic push-down automata. So this is a deterministic Turing machine. This is a deterministic Turing machine, right? Now the other one is non-deterministic Turing machine. Now the other one is non-deterministic Turing machine. Now the other one is non-deterministic Turing machine. Other one is non-deterministic Turing machine, right? Now how does non-deterministic Turing machine look like? Delta is q cross tau, which means if I am in a state and if I see some symbol in input alphabet, tape alphabet, tape alphabet, tape alphabet. I will go to any number of states. I will make many copies of myself, and one copy of myself will go to one state, other copy of myself will go to other state, multiple copies will be created. That is why we are writing 2 power. It can go to any number of states, and it can write, every state will get a different tape, and it will write a different tape alphabet, different tape symbol, and then it can move left or right, and then it can move left or right, and then it can move left or right. Okay, so this is non-deterministic Turing machine. This is non-deterministic Turing machine, right? Now one thing you have to observe here is deterministic Turing machine and non-deterministic Turing machine are equal in power, right? So let us see what are the machines that we have seen so far. One is, we have seen finite automata, right? In finite automata we had deterministic finite automata and non-deterministic finite automata, right? If you remember finite automata, we have DFA and NFA. In case of DFA and NFA, both are equivalent in power. In case of DFA and NFA, both are equivalent in power, right? In case of push-down automata, deterministic push-down automata is less in power compared to non-deterministic push-down automata. Non-deterministic push-down automata compared to deterministic push-down automata is less in power compared to non-deterministic push-down automata. Deterministic push-down automata is less in power compared to non-deterministic push-down automata. Compared to non-deterministic push-down automata, right? 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 Now coming to deterministic Turing machine is equivalent in power to non-deterministic Turing machine. Deterministic Turing machine is equivalent in power to non-deterministic Turing machine. Non-deterministic Turing machine. Non-deterministic Turing machine. Right? Now how will a Turing machine accept a string? How will a Turing machine accept a string? How will a Turing machine accept a string? If it reaches final state. If it reaches final state and stops there, right? And how will a Turing machine reject a string? It will reject a string if it does not stop in final state and it comes across dead configuration. I will show you what is dead configuration is, right? Even when you reach to final state also, sometimes you may get dead configuration. And second way of rejecting is it will hang. It will hang. It will not stop. It will hang. It will not stop. It will hang. Okay. Okay. So there is an algorithm. There is an algorithm. We are not going to study this. This is not important. There is an algorithm to convert. There is an algorithm to convert. There is an algorithm to convert non-deterministic Turing machine to deterministic Turing machine, right? Now we are able to convert any non-deterministic Turing machine to deterministic Turing machine. Therefore, non-deterministic Turing machine is not powerful than deterministic Turing machine, right? So what can you say? This problem is decidable. Whenever there is an algorithm, the problem is decidable. Converting a Turing machine from non-deterministic Turing machine to deterministic Turing machine, this is a decidable problem. 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 Right? Right? So, standard Turing machine is deterministic Turing machine. Standard Turing machine is deterministic Turing machine, right? A Turing machine may halt. A Turing machine may halt or it may hang. A Turing machine may halt or it may hang. A Turing machine may halt or it may hang. It may hang, right? When it halts, if it halts in final state, we will accept. If it halts in final state, we will accept. If it halts in non-final state, it will reject. If it halts in non-final state, it will reject. Now, if it hangs, this string is rejected. If it hangs, this string is rejected. This string is rejected, right? So, if you look at recursive language, recursive language corresponds to halting Turing machine. Recursive language corresponds to halting Turing machine, and recursively enumerable language corresponds to Turing machine. We are not saying halting Turing machine, we are just saying Turing machine, which means the Turing machine may not halt, it may hang. Okay, fine. So we will start with the Turing machines tomorrow. Okay, we will end the class here. We will start with the Turing machines tomorrow. Tomorrow the class is going to be very, very interesting. Don't miss the class. Okay, it will be very, very interesting, like finite automata and push down automata. Turing machines, we are going to solve a lot of problems. They are going to be very, very interesting. See you tomorrow. Good night, everyone. Thank you.